In this video, we're actually going to dive inside the atom and look at the subatomic particles that constitute the atom. The main reason we're concerned with subatomic particles as chemists is that they allow us to index and categorize the elements. We'll see that different elements contain atoms with different numbers of subatomic particles. They're also interesting from a charge point of view, since some of the subatomic particles have charge. So let's jump right into it with the constituents of the atom. Now, the first thing to say, and you may have heard this in the past, is that the atom is mostly empty space. The mass of the atom is highly concentrated at the center in a region that we call the nucleus. And I love this size comparison to give you or metaphor to give you a sense of the size of the nucleus. If the atom were the size of a football stadium, the nucleus would be about the size of a single blueberry sitting at the 50-yard line of the football field. This gives you a sense that the vast majority, all the mass of the atom is concentrated in that blueberry. Everything else in the stadium, empty space. In the nucleus, we have two types of subatomic particles, and there's a third particle that exists sort of surrounding the nucleus. Protons are really the key particles in the nucleus. They have positive charge. They're in that nucleus, and they're often represented as P+, especially in a particle physics context, the plus indicating positive charge and P for proton. Those sit in the nucleus. The nucleus also contains neutral particles with the same mass as the proton. These are known as neutrons. They don't affect charge in the atom at all, but they do profoundly affect mass. One thing I'll point out now is that the proton and neutron are much heavier than our third subatomic particle in the atom, which is known as an electron. Electrons are negatively charged, and they surround the nucleus. They exist in that mostly empty space in the football stadium, right? They're wandering around the stadium with that blueberry of a nucleus sitting on the 50-yard line. And so this is essentially our most basic model of the atom. It contains three types of subatomic particles: positive protons and neutral neutrons in the nucleus, and negatively charged electrons surrounding the nucleus. The number of protons in the nucleus is actually what defines the elements. All atoms of a particular element have the same number of protons in the nucleus. And that number of protons in the nucleus has a very special name. It's known as the atomic number, and it's represented with the symbol capital Z. The nucleus can also contain neutrons, and in many cases we're interested in the total mass of the nucleus, or the total count of protons and neutrons in the nucleus. This is known as the mass number, and it's often represented with a capital M or sometimes a capital A. And I just made this point, but to hit it again, atomic number defines the elements. So if you have two atoms that both have 6 protons, those two atoms belong to the same element, and two atoms with different numbers of protons belong to different elements. Atomic number defines the elements, and this is why it has the name atomic number. However, it is possible for two atoms of an element with the same atomic number to have different mass numbers due to different numbers of neutrons in the nucleus. And examples of these types of atoms are shown at the bottom of this slide. All three of these atoms correspond to neutral hydrogen atoms. We have one proton in the nucleus and one electron surrounding the nucleus. But the three atoms differ in the number of electrons in the nucleus. The first atom has 0 neutrons in the nucleus, the one in the middle has 1, and the one here has 2 neutrons. So these are all atoms of hydrogen, but they differ in mass number. Right? They have identical atomic numbers. Z is 1 for all of these, but they differ in mass number. And atoms of this type are known as isotopes. Same element because they have the same atomic number, but different mass numbers due to the different number of neutrons in the nucleus. And again, here I'm just surveying the mass numbers and atomic numbers that we reviewed. Atomic number is 1 in all cases because we have 1 proton in the nucleus in each case, but the mass number goes from 1 to 2 to 3. This atom is known as hydrogen 1, this is hydrogen 2, and this is hydrogen 3. Now, this is a bit of a clunky representation, especially for the not artistically inclined, and we'd like a textual way to represent a particular isotope of an atom with its atomic number and mass number. We do this using an atomic symbol. Now, you probably know from everyday life, and if you've ever looked at a periodic table, that each element has an element symbol. This is one or two letters starting with a capital letter, and that symbol is used to signify atoms of that element or a bulk sample of the element. In an atomic symbol, we use superscripts and subscripts to represent the mass number and atomic number respectively. And there's a convention here as far as where we put stuff. So the bulk of an atomic symbol is just the element symbol. Here's the symbol for chlorine, for example, Cl. The atomic number of chlorine is 17, and that goes in the bottom left as a subscript to the left of the element symbol. The mass number of this particular atom of chlorine or sample of chlorine atoms is 37, and this is the total number of protons and neutrons. And this thing as a whole is the atomic symbol for chlorine 37, the isotope of chlorine specifically with the mass number 37. One thing to point out here about atomic symbols is that the atomic number in the bottom left is actually redundant with the element symbol, right? Cl, every atom of Cl has 17 protons in the nucleus, and so it's not really necessary to include this 17 if I know or can look up the atomic number of chlorine. Sometimes it's done, though, to make it easy to determine the number of neutrons in the nucleus. Since the atomic number is the number of protons and the mass number is the number of protons plus neutrons, the difference between these two numbers is the number of neutrons in the nucleus. And this becomes a simple subtraction problem, right? It's even nicely visually laid out to determine the number of neutrons when things are laid out this way in the atomic symbol. The last thing we want to think about here are ions. In a neutral atom, the positive charge of the protons in the nucleus is balanced by the negative charge of the electrons. So those hydrogen atoms we looked at earlier, for example, we have positive 1 due to the proton in the nucleus and negative 1 due to the electron surrounding that nucleus. So the overall charge of the atom is neutral. Atoms with an unequal number of protons and electrons have a net charge, and these are known as ions. There are two general classes of ions. Cations have net positive charge, and anions have net negative charge, and the reason for this has to do with the relative number of electrons and protons. Cations contain fewer electrons than protons, so there's positive charge in the nucleus that isn't completely counterbalanced by negative charge due to the electrons. Anions have more electrons than protons, so the negative charge of the electrons is not completely counterbalanced by the positive charge in the nucleus. Cations we represent with a plus symbol, and anions with a minus symbol. And ions can actually consist of multiple atoms. Here we're going to focus on the so-called monatomic ions, which contain only one atom in the ion. But multiple atoms can be bonded together and still have a net charge, and these are known as polyatomic ions. In an atomic or ionic, we might say, symbol, we represent the charge in the upper right as a superscript to the right of the element symbol, using either a plus or minus, or 2 plus for a positive 2 charge, 3 plus for a positive 3 charge, 2 minus for a negative 2 charge, 3 minus for a negative 3 charge, etc. And an interesting thing to point out here, well, the first thing I'll note is we've actually omitted in these two examples at the bottom of the slide the atomic number, since this follows from the element symbol. Every atom of zinc, whether it's neutral or charged, has an atomic number of 30, for example. And another thing to note here is that the charge implies the number of electrons. Because I know this is zinc and there are 30 protons in the nucleus, that's plus 30 in the nucleus due to the positively charged protons. For the ion to have a plus 2 charge overall, I need a negative 28 charge from all the electrons. And so the plus 2 charge implies 28 electrons in the ion, since 30 minus 28 is positive 2. In the second example here on the right, we have Br minus, and the mass number is 81. Again, the atomic number is implied by the fact that this is bromine. Every atom of bromine, be it neutral or charged, has an atomic number of 35. The -1 charge right here implies the number of electrons. Since we have a -1 charge overall, positive 35 due to the 35 protons in the nucleus, this tells me that there are 36 electrons in this ion. -36 due to the electrons, but only positive 35 due to the protons in the nucleus gives a net charge of -1. So this gives you a sense of how we can represent ions using atomic symbols. It's less common to include mass numbers in these ionic symbols, but you may see it, and it uses the same convention that we saw in the previous slide for neutral atoms. You'll see this regularly, especially where isotopes are involved. If we need to distinguish between two atoms of an element with different mass numbers, we'll often do that by including the mass number as a superscript to the left of the element symbol. Let's end here with our first set of lingering questions about the atomic theory, atoms, and the representations of atoms and ions. The first question here is, how do we think about atomic mass in a macroscopic sample of an element with multiple isotopes? If we roll back to the atomic theory, it's actually a little bit interesting, now that we've discussed isotopes, to think about this idea right here, that the mass that is characteristic of an element is the same for all atoms of that element. We've seen that actually the mass in the nucleus can vary for atoms of the same element. Hydrogen 2 is about twice as heavy as hydrogen 1, for example, but a macroscopic sample of hydrogen could contain a mixture of these three different types of isotopes. So how do we deal with that on the macroscopic scale, where we're dealing with an unfathomably huge number of atoms distributed over various types of isotopes? The second question is about the charges of the monatomic ions. Do these follow any sort of pattern? How did I know to write zinc 2+? How did I know to write bromine 1-? These do follow a pattern, and it's one that you'll encounter in your introductory chemistry course, and one that we'll actually refer to a little bit later as we get into nomenclature. What about the chemical properties of isotopes, right? Hydrogen 1, hydrogen 2, hydrogen 3, how similar are they? Do they do the same reactions? Do they display the same chemistry? Do they form the same compounds? Can we separate different isotopes? If we have a sample that consists of hydrogen 1 and hydrogen 2, can we separate out the hydrogen 2? How might we think about doing that? This is a question that is actually very subtle, and one that you may or may not see in future work in chemistry courses, but it's an interesting one to explore on your own. I actually deliberately avoided using the word orbit in this video to sort of avoid giving you the preconceived notion that electrons orbit the nucleus, but this is a very common representation of the atom that you'll see, right, with the nucleus in the middle and oval-shaped orbits of the electrons around the nucleus, right? There's this popular idea that electrons orbit the nucleus like planets around the sun. But it's not really what electrons look like. And as you advance in your studies, you'll get more insight into what an electron really looks like at the unfathomably small scale of a single atom.